Awesome. So I want to sort of carrying on the theme of being a bit chaotic with my coats, um, but also I think in general in our industry we do tend to see more chaos than we might like, and I think thinking about lockdown and thinking about this year has made me reflect a bit on how lucky we are in software engineering, because we really were able to take our jobs in most cases and just move them remote, and things kind of worked. And in general, some people have said, if it had been 5 years ago, we couldn't have done that transformation. And without all of the digitization that we have and without the cloud, it would have been so much more disruptive. And I think so there's that sort of 2020 aspect to technology makes things better. But I think in general as well, this is such a good time to be a software engineer, whether there's a lockdown or not. And I do a lot of work with the cloud, and it makes me so happy that I work with the cloud, because I really, on the theme of love, I love the cloud. It makes things so much nicer. It makes things so much easier. But even though everything is in general better with the cloud, there are a few points when things go wrong, and the cloud is the thing that made it go wrong. We were talking before this session about the way you program for the cloud is really different from how you used to program. And for those of us who are a bit old and who've been in the industry for a while, there was sort of an adjustment that we had to do for the cloud, because really, it changes things. But I think even for those of us who are maybe newer to software engineering, what we're seeing is that the ecosystem is still catching up with the implications of the cloud. And so sometimes things change really rapidly, or sometimes things just aren't optimized for the cloud in the way that you'd hope they would be in 2020. And there are a lot of things that we need to be doing well as software engineers in 2020. The main one is hand washing, whether we're a software engineer or not. But as software engineers, a lot of us are writing apps. That's our job. But it's not enough to be writing apps anymore. That's one of the things that the cloud has changed. So we need to be looking at that ops side of it as well. And as well as ops, of course, it's not, once you're doing the apps and the ops, then you're doing DevOps. And again, in 2020, even DevOps, actually, that's kind of 10 years old. We need to be moving on from that, and we need to be doing DevSecOps. And even DevSecOps actually isn't enough. And there's DevSec BizOps and Design Ops and various DevSec Biz Design Ops, various permutations. And I won't go through all of them. But there's one that I do want to call out, which is phinops, because I think as we move more and more to the cloud, phinops is becoming really important. So I'll talk a little bit more about that. But overall, with all of these things, the reason we're seeing these shifts is because, like I said, the cloud changed so many things, and a lot of things that we sort of knew were true ended up just being the opposite in the cloud. So I want to talk about some of the things that are different in the cloud that we need to be looking at differently, and that we need to be pushing our vendors to do differently. The first is management. So it used to be that it was really easy to keep track of your servers, because you had a fairly small number and they lived in a data center. And if you wanted to know how many you had, you could walk up and go 1, 2, 3, 4 server. But now with the cloud, it seems like we can have unlimited hardware. It's so easy to provision the hardware. But of course, just because it's easy to provision the hardware doesn't mean it's easy to keep track of the hardware. It definitely doesn't mean that hardware is free. It's going to be in someone else's data center somewhere using electricity. And the thing about the cloud is because we didn't really put any effort into provisioning the thing on the cloud, it's often we make things that aren't useful, which is kind of sad. And these things that aren't useful just sort of sometimes have an indefinite life, and they just keep going on and on and on. And I think, we've all had this experience. When I was first learning Kubernetes, of course, I tried it out because how else are you going to learn it? So I created a cluster. But I had too much work in progress, so I got pulled away to something else, and I forgot about this cluster that I'd made. And it was a fairly high-spec cluster, so it was €1,000 a month, this cluster. So that was quite an awkward conversation with my boss when I had to sort of go back and say, oh, yeah, I just burnt €2,000 doing nothing useful. And it's not just me. Our industry has a really horrible problem with zombies. Almost every organization has servers that are somewhere that are still consuming electricity, still consuming cycles, but just not doing anything useful. And that's bad. And in terms of quantifying how bad the zombie problem is, one of the reasons the zombies are zombies is because we don't notice them, we don't remember them, we don't see about them. But people have done surveys and they've systematically gone through servers to try and figure out, well, how many of them are doing useful work. And in one survey, they did it in 2017, and they found a quarter of the servers, and they looked at 16,000, so it was a decent sized survey. A quarter of them were doing no useful work. And when the authors sort of looked in to try and figure out, well, how did this happen? How can you have a quarter of your servers not doing any useful work? They concluded that perhaps someone forgot to turn them off. And, we do end up with this enormous expense coming just from forgetfulness. So this is where phinops comes in. And there's a few definitions of phinops. The official definition is about making sure that you have automation for your financial management and making sure that there's accountability for the costs so that the costs flow to the right business unit in an easy, frictionless way. But I like to think of phinops as basically figuring out who in your company forgot to turn off their cloud, because that's the sort of the visibility that it enables. Another thing that's really different in the cloud, or at least in the cloud style architectures, is tracing. So it used to be we'd have one set of logs. Now we have our logs spread everywhere. So we need to be looking at things like distributed tracing. Another thing that's different is packaging. So I used to work on WebSphere, and we used to have big debates about what was the best way to package your application. Did you want to wrap it all up in a jar? Did you want to have it as sort of a big fat jar? Did you want to have sort of a small unit that was easier to share? What was the best thing? The cloud has pretty much made that debate go away. Fat jars behave really badly with a layered container system. You want to have minimum change at the bottom and very small slivers that change often at the top. So that fat jar idea, I think, now really doesn't make so much sense. How we think about performance has changed as well. So in an ideal world, everything would just go as fast as possible. But of course, that's not how it ever works. Performance tuning is always about trade-offs. It's about figuring out what your use case is and optimizing for that use case, perhaps at the expense of other use cases. And one of the things that we didn't used to optimize for so much was footprint. But in the cloud, your memory footprint is money, because these things are getting stacked really highly. And if you can't stack them densely, you're going to pay for that. And it used to be that a Java application would start, and then maybe 6 months later, someone might restart it. But of course, now these things are going up and down really often. So that startup time matters a lot. We don't want to optimize for throughput post startup. I mean, we want that to be good, but we also need to consider the startup time. And that changes some of the things that used to be a good idea and used to not be a good idea. So it used to be that ahead of time compilation in Java seemed like a good idea, but was actually a really bad idea, because you can make a smarter optimization if you observe a program running at runtime than you can ahead of time. But now, because we have that pressure on the startup times, we've switched, and ahead of time compilation really makes a lot of sense. And if you look at some of the things like Quarkus, what they can achieve in terms of these sort of millisecond startup times for a Java application, and these sort of tiny footprints, it's really incredible. And so I'm sort of, I find that fascinating to sort of see how the things that we can achieve now that we have the need for them. Another thing that's changed a lot, and this is one that I sort of get really agitated about sometimes when I talk to clients, is releasing. Because it used to be that we were burning software to a CD. That was really expensive. We didn't do it very often, and it had to be right when we did it. But now we can release many times a minute. And so the pressures of what we want to optimize for are different, but the business hasn't always caught up. And so sometimes we do still see these really sort of rigid scheduled releases with quite a lot getting shoved into each release, which doesn't really do much for system resilience or for consumers or for site reliability. And like I said, I think, the business has been slow to catch up on this, because the things that used to reduce risk now increase risk. So things like infrequent releases, things like release boards, there was a good reason those were there, but now they're actually harming quality. So the Garage spoke to a bank in Asia Pacific, and this was a sort of a well-established bank, and they realized that they were getting their lunch eaten by their competitors, and the reason was that they were moving way too slowly. So they said, we've got this big COBOL estate, we need to modernize it, which was a good idea. We need to split it into microservices, which was probably a good idea. And we said, great, yeah, we can help you. This sounds really good. And then they added, our release board only meets twice a year. So if your release board only meets twice a year, it doesn't matter how many microservices you have, they're going to go out twice a year. So you're paying the cost of that architecture without the benefit. And really what microservices are trying to give you is that modularity, and that's the goal. Microservices on their own aren't the goal, and there's lots of ways to achieve modularity, only some of which are microservices. So microservices are a means. And what I see with microservices in particular is something that I call wishful mimicry. So this is, we look at the industry leaders, like, we say, oh, Netflix, they have such a fantastic engineering culture, which they do, and they use a lot of microservices. If I adopt microservices, I'll be doing what Netflix does, so I'll be as good as Netflix. And I think, well, that's not necessarily true. There's a whole bunch of context for Netflix that makes microservices make sense, that may not make it make sense in other contexts. And as well, there's a whole bunch of engineering practices that they've adopted alongside the microservices. So microservices on their own may just cause chaos. And I think we sometimes feel that in order to be like really good and, in order to be really cloud native and, to be cool with the cloud, we have to be doing microservices. Cloud enables microservices, but it's not necessary. And we do see a lot of cost with microservices. We do see challenges, and we do see cases where they don't live up to their promise. So I worked with a client, and they called me in because their starting point was, every time we touch one microservice, all the others break. And of course, this is the exact opposite of the promise of microservices, which is that they're supposed to be really independent. But they just ended up with basically this distributed monolith, and it just sort of, it didn't have the compile time checking that you might get in an actual monolith. And it had all of the distributed computing challenges in terms of, my service might go away, I don't get guaranteed function execution, I can't do two-phase commit. And yet and the complexity of the system was just, it was bad. There was a lot of complexity. So in that case, microservice, it didn't help the core problem. And in general, we can't assume that distribution helps. So this is one of my favorite examples of a distributed system. This is the Mars Climate Explorer. And it kind of looks like it's made out of like a garbage bag and duct tape, but I think it actually was really well engineered. And despite that, it did have one fatal engineering problem, which meant that it had a rather sad end. And instead of orbiting around Mars, which was the intention, it went ploop into Mars. And the reason was because of distribution. So it had two control systems. One was on the actual Climate Explorer, and that would do the sort of the small adjustments. And about every 2 days, it would come into view of Earth, and the Earth controller would send it some adjustments and some course corrections. And problems happened because the Climate Explorer, they were done by 2 different teams living the microservices dream. The Climate Explorer itself was using metric units. The unit on the Earth was using imperial units. They were, for this particular unit, they were sort of the same order of magnitude. So nobody noticed the problem until the Climate Explorer was on the surface of Mars. So I think it is safe to say, in this case, having 2 different teams develop the software and having it be distributed, I mean, it was about as distributed as it can be. One of it was in space, did not help. And fundamentally, we sometimes equate being distributed with being decoupled, but you can be massively, spaghettifully coupled while still being distributed. So when evaluating microservices, there's really good reasons to do microservices, but there's a whole lot of reasons not to do microservices as well that we need to, so you need to take into account both sides when making a decision. If it's a small team, it's not worth it. If you're never planning to release the parts of the system independently, it's probably not worth taking the overhead of distribution. When you have microservices, you need to look at how they're going to find each other, how communication between them is going to be secured. And the thing that will in general solve those problems for you is a service mesh. And I think some people hear service mesh and they sort of go, ooh, service mesh, that's a bit heavy, tricky. I don't think I want a service mesh. Instead, I'll write something to handle those concerns. And of course, at that point, you have a service mesh. It's just that you wrote it yourself and you have to maintain it yourself, which may not be what you actually want. And another reason is that the domain model may not split nicely. So in the case where the microservices were super coupled and touching one broke everything else, when I looked into it, when I looked at the code, I could see the same code cut and pasted across every service. And it had been cut and pasted rather than pulled out in a library to avoid coupling. But the system was really sensitive to changes. So it was still coupled. It was just kind of a hidden coupling. And it was because the domain actually encompassed all of the microservices. So the ideal is that you have a whole bunch of microservices and each one has its own domain. But in this case, the domain was for all of them, which was bad. So everybody always says, and it's totally true, if you're going to do microservices, you need to get good at automation. The other thing that you need to get good at is testing. So I like to think about the test pyramid. When I first read the test pyramid, I sort of thought, oh, this makes so much sense. So at the top of the test pyramid are your integration tests. They give you great confidence. They're an end-to-end test. They give you great confidence that the system works. There's a problem, which is that they're really expensive to write, they're expensive to run, they're expensive to maintain. So you don't want a lot of them. At the bottom of the pyramid are unit tests. They're delightfully cheap to run, really cheap to write, but they've got a small problem, which is that they don't necessarily give you much confidence that the system actually works when it's put together. So this is where contract tests come in. And there was an earlier talk about contract-driven development as well by Devin. And, this is something that pay attention to it. And the good thing about all of this as well is you can do test-driven development at every level. So I really like to do contract-driven development. So when we think about what a contract test does and how it fits in, if you think about a fire alarm, the way that you test a fire alarm is not this. This gives you great confidence that the fire alarm works, and you hope that the manufacturer tested it at least once this way. But I am not going to set my house on fire once a week to know that my fire alarm works, because then my house is on fire. So confidence, but really too expensive. At the other end of the pyramid, every fire alarm has this little button that says test and push. And so once a week, you can push that button and it will go beep, beep, beep. And that's basically unit testing a fire alarm. And that gives you a lot of confidence that the fire alarm can go beep, beep, beep. But of course, I want my fire alarm to do more than go beep. I want it to go beep when the house is on fire. So there's kind of an intermediate step. And this is where contract testing comes in. So you don't see them in households, but institutions will have these tests for their fire alarms. And it's sort of like a cup. And inside the cup, it sort of hisses out a gas that's like, well, smoke, basically. And then once that's done, the fire alarm goes beep, and everybody knows that actually the two bits work together, and we have the confidence. So let me show you a little bit of what this would look like in practice. This is going to be the world's fastest demo, but I will be sharing the code for it as well. So I have a demo, and I like to have a house as a model for microservices, because your data sort of goes from room to room and it gets a transformation in each room. So if I reload, you can sort of see some of those transformations, which is that you start up and, you wake up in the morning and your hair's like, poof, and, then you go to the bathroom and you brush your hair, and then you go to the kitchen and you eat, so you get a bit fat. And then at the end of the day, you go back to the bedroom and you fall asleep. So this is my application. And if I look at I can see that if I call my back end, I've got just a little data model coming back with body parts and the state of each body part. And if I look at the code, if you're paying a lot of attention here, you'll notice that microservices is probably pushing it. I have a front end and I have a BFF, which, because this is a person, is best friend forever, not back end for front end. And so it's actually only two parts. But the principle ends up being pretty similar between a front end and a back end, as it does with a more complex system, just with more complexity. And because I'm running this live and trying to stream at the same time, I didn't want the complexity of 18 services. And I can show the principles exactly as the same. So what I've got is I've got my front end, which is written in JavaScript. I have a back end, which is
Olivia, seeing your slides.
Thank you. Thank you. Let me fix that. I'm glad you said now rather than after 7 minutes of me talking to myself. Right, so let's try that again. Okay, so we have our application, which has the house, and you can see the resident sort of moves through each part, having those state changes. I have this panel on the right-hand side just for debugging. If I look at the data model, I've got a bit of JSON. And then looking at the code, I have a front end, which is just a little React application. And then I have a back end, which is a micro profile application. And the key thing is that I have a resident. And so that resident is sort of where my data model lives. And had I done more distribution, the resident would be sort of pulled together from different parts. But I want to show now where the contracts come in. And contract testing gives you three really useful things. The main one is it gives you the confidence that your system works together. But for the front end, for the consumer, which in this case is the front end, it acts as a mock, so that as well as, or instead of writing your own mock, you can just use the contract provider as a mock, and then that allows you to drive your code. On the provider side, it gives you a really strong validation. So you still want to have some other tests, but running your contract tests will give you some pretty strong validation of the semantics, not just the syntax. So there's various contract providers. What I'm going to show here is Pact, which I like because it's cross-language and because it does give you that really strong validation that you're not just looking at the syntax, you're actually looking at things like, if I pass in this message, I expect to get a message that looks like this back, whereas if I change this parameter on the input, this parameter should be different on the output. So I have I have a unit test here, which is just using a mock for my HTTP. And for simplicity, what I did is I just cut and pasted my unit test to be my contract test. You probably wouldn't do that normally. You'd want to have different things in each one, but I think I found it helpful to sort of show the similarities between them. And if I'm just going to sneakily delete this so that we can have the fun of watching it reappear. And so if I run my tests, you can see that it ran them all and my pact has come back. And so this is a JSON specification, which is generated by, you can generate it by hand, but it's nicer to have it generated by the tests to say things like, if I call get and pass in resident, then I'm going to get something that looks like this. And so this is sort of an example data. And then here's some rules that say, well, the hair can be frizzled or combed, that kind of thing. So why is that useful? And I can do the same thing on the server side. So on the server side, I have a house contract test, and you can see that this is a tiny test, which is one of the nice things, is all of those interactions are just being automatically validated with just a few little lines of code. And if I run this, we can see that it should run successfully. And it runs successfully. Cool. So, but in my resident data model, I've got a torso. And that's kind of, I'm not sure if that's the most accessible word. So I'm going to do a refactoring. And I'm going to call it stomach instead. Oops. And so this seems like quite an innocent little refactoring. I've made the code better, yay me. But if I go to my data model, you can see what's coming in on the wire in the JSON has changed. And so if I go to my application, you can see that here, it's not strongly coupled to the data model, so that still works fine. But here, I had this quite necessary coupling to the name of the image for the body part and the data model. So even though I thought I'd made this innocent change, I broke my application and I didn't know. But had I run my tests before deploying my change, I would have seen that I've got a comparison failure and it's saying, no, I should have had a torso rather than a state. So with that, the super quick tour of contract testing, just to, as you know, as sort of a concluding point, really, I would really encourage you to look into consumer-driven contract tests if you're looking at microservices as a way of kind of damping down some of the chaos. And finally, like I said, the code is available. I'll be heading over to Spatial. We can have some questions on Discord as well. Welcome questions by Twitter. And thank you very much.